Thank you very much for inviting me. It's a pleasure being here. I haven't been in Berlin for many years. Particularly in this weather, because we have had a heat spell. So on average, I'm fine. I'm feeling fine. Okay, what I want to talk about is the following. I want to talk about the role of the sun, and in particular discuss the idea that the sun affects the climate through cosmic rays, or at least there's a large effect through cosmic rays. I'm not going to discuss the general evidence that shows that the sun does affect climate. I'll take it for granted because we're actually going to hear some more presentations discussing it later. I'll just mention a few, or maybe 2 slides about it. This is the results from the Heidelberg group that Professor Zinger mentioned. What we see here is a reconstruction of what the sun has been doing over the past several thousand years, and what, or a climate proxy. Specifically, you see carbon-14 from tree rings, which is affected by cosmic rays, which is affected by solar activity. I'll probably get into it in a little bit. I'll explain exactly how the relation arises. And oxygen-18 is, or the oxygen-18 to oxygen-16 isotope ratio is a proxy for climate because water with oxygen-18 is heavier than water with oxygen-16, so the evaporation rate from the oceans is different. So you get fractionations, whatever. It doesn't matter, the details are not very important. What is important is the fact that you have a very nice correlation between solar activity on one hand and a climate proxy on the other hand. In this case, it's the climate of around the Indian Ocean. Here we see another analysis. This work was by the Bond et al. Group. We see here something similar. We see a correlation between solar activity. You see here again the carbon-14 in blue, and in black you see sedimentation records from the bottom of the ocean, basically telling you whether the northern Atlantic was cold and you had icebergs drifting further south, or you didn't have that. So it's a climate in a totally different area on Earth, and again you see how it's affected by the sun. So there are very good indicators that the sun affects the climate, and what I want to discuss is this question is what I want to discuss. First of all, we want to discuss how this effect arises. And then we want to discuss how much is this effect. We want to quantify it, because if we want to understand quantitatively what has happened, for example, over the 20th century, we need to quantify the effects of the sun. And then once we do understand it qualitatively and quantitatively, we can better understand what it all implies with respect to 20th century global warming, with respect to 21st century temperature change, etc. Okay, so what I want to concentrate is the fact that although there are several methods which can affect the climate, or several means, the one which is probably the largest and the dominant one is the fact through cosmic rays, is the effect through cosmic rays, which I'll discuss in a second, all the evidence. Then I'm going to show you that you can quantify the effect of the sun, and then you find that it is very large. Quantitatively, it's 1 watt per square meter for over the 11-year solar cycle, or over the 20th century, which is very large because it's comparable to all the other effects that we have. And then I want to show you that part of the 20th century is warming is human, but a large part is also because of the sun. And once you understand that, you realize that it goes hand in hand with the fact that climate sensitivity is on the low side, which is what Professor Zinger said before. Climate is much the response of the climate to changes in the energy budget, whether it is because of CO2 changes or because of solar activity changes or because whatever, is on the low sides. There are no positive feedbacks which want to amplify it. Okay, and then the bottom line is going to be that the temperature increase over the 21st century, if we manage to double the amount of CO2, is going to be of order 1 degree. This, of course, is if you're pessimistic and you think that we'll actually be able to double the amount of CO2. I'm personally optimistic that for very other reasons, for good reasons, over the next decades, we'll switch to alternative energy sources, but in due time and for the right reasons. Okay, so what is the cosmic ray climate link? We'll first discuss what is the link, then we'll try to see what is the evidence. I'm going to try and prove to you that this link actually takes place. So what is the link? Well, the sun is a star which changes its activity. Sometimes it's not very active, sometimes it's more active. It changes its luminosity, its irradiance by something like 0.1% over the 11-year solar cycle. The 11-year solar cycle arises because it takes every 11 years the magnetic field of the sun switches polarity. And you have also long-term secular variations in the solar activity. For example, over the 20th century, solar activity has increased. So you have the 11-year solar cycle and you have long-term secular variations. When the sun changes its activity, not only does its irradiance change by, say, 0.1%, but you also have large variations in other things. For example, in the amount of X-rays it emits, in the amount of UV, in the solar wind, the wind that is responsible for comets' tails. In all those things, you have large variations. And in particular, you have a large variation in the solar wind. The solar wind is a tenuous wind of actual material. When it reaches the Earth, for example, we can see it in the form of aurora near the magnetic poles. But what's interesting is that this solar wind acts as a barrier for high-energy particles which are coming from outside the solar system. We are constantly being bombarded by high-energy particles from a GeV and more. And these particles, which are called cosmic rays, they come from the death of massive stars, which takes place all over the Milky Way. These particles roam the Milky Way, and when they reach the solar system, they have to diffuse through the winds of that the sun generates. And these particles lose energy, and what happens is that when the wind is stronger, less of these particles reach the Earth, and we get less of them. Now, the interesting thing about the cosmic rays is that they are the dominant source of ionization in the atmosphere. Here in the room, we may have ionization which is governed by the amount of radon which comes out of the, well, this is not concrete, so you don't get radon out of that, but we have radon gas and we'll have ionization here from the radon, but if you go out, the dominant source of ionization in the troposphere is these high-energy particles which are coming from outside the solar system. Now, when the sun is more active, you have a stronger solar wind, then less of these particles can reach the Earth, and what you get is that the amount of ionization in the atmosphere, the number of ions that we form, is going to be lower. Now, it was suggested already in 1959 that there may be climatic variables which are sensitive to the amount of ions that we have in the atmosphere. It was theoretically suggested in 1975 that the formation of cloud condensation nuclei could be affected by the ionization. And it was demonstrated about a decade ago by the Danish group that indeed cloud cover characteristics change in the course of the 11-year solar cycle. So the link is solar activity, solar winds, cosmic rays, change in ionization, change in cloud characteristics. And we know today that when the sun is more active, we have less cosmic rays, less ionization, less numerous cloud condensation nuclei, and we get, when the sun is more active, clouds with fewer droplets which are larger. They have a smaller total surface area, and therefore they are less white. And if they are less white, they reflect less of the sunlight and they hit the Earth. That's the link. Okay, and then you'll get something which appears like a correlation between solar activity on one hand and climate on Earth, the temperature on Earth, but the actual link is relatively indirect, but there's evidence for all the components. Okay, this is the correlation which was found in 1998 and extended with more data which came later. What you see here are changes in the cloud cover in blue and changes in the cosmic ray flux reaching the Earth. And you see that the two correlate very nicely. You see that the cloud cover changes together with the changes with 11-year solar cycle. The problem with such a correlation, it proves beyond doubt that the sun affects the climate. But it doesn't prove that the effect is necessarily because of cosmic rays, because you could have in principle that the sun affects cosmic rays and that the sun affects climate by some other mean, and you'll get a correlation between the cosmic rays and the climate without a causal link. So in order to prove that, you want to find changes in the cosmic ray flux which are independent of solar activity, or which are so unique to the cosmic rays, even if they do originate from solar activity, that you'll be able to say, aha, this is a fingerprint of cosmic ray flux. So what I want to show you now is all the evidence that gives you this fingerprint that indeed it is the cosmic rays which are affecting the climate. Okay, so one result is the following. Over the past 550 million years, you can reconstruct the climate using, again, the ratio between oxygen 18 to oxygen 16. This case, it is from brachiopods. So it's fossils of animals which lived in tropical oceans. And you can reconstruct the temperature and see here in black that the temperature over the past 550 million years oscillated with a periodicity of about 150, somewhat less than 150 million years. On the other hand, you can reconstruct the cosmic ray flux using iron meteorites. Basically, iron meteorites break off their parent bodies, they roam the solar system, and between the time they break off their parent bodies and the time they fall on Earth, they record the historic variations of the cosmic ray flux. So you can use these iron meteorites to see exactly how the cosmic ray flux has changed over the past billion years, and you can see these the same cycles. Now, what is the origin of these cycles? The origin of these cycles is the fact that the Milky Way is not homogeneous. The Milky Way has spiral arms, and it is the spiral arms where we have most of the star formation and most of the death of massive stars which produce the cosmic rays. So every time the solar system passes a spiral arm of the Milky Way, which takes place every just less than 150 million years, we see an increase in the cosmic ray flux, and at the same time on Earth, it's colder because you have allegedly more clouds and it's colder. This is a much more recent result, again coming from the Danish group. What you see here, these are the changes in different climate variables following things which are called Forbush decreases. Forbush decreases are several day-long decreases, which you can see here in red, of the cosmic ray flux which reaches the Earth, and they originate from the sun. The sun can have a flare, and this flare it's a gust, it will generate a gust in the winds, and because of this gust in the wind, we'll get less cosmic rays reaching the Earth, and you'll get a decrease in the cosmic ray flux reaching the Earth. Now, what do you see when you look at different climatic variables? You see that following a large decrease in the cosmic ray flux, you see changes in the characteristics of the aerosols, or the condensation nuclei that you form. You see a change in the, these are three different cloud data sets from different satellites looking at things like the total water content, the total cloud cover, etc. And you see that in all these data sets, you can see that together or concurrently or following the Forbush decreases, you see a change in the cloud parameters. So it's a fingerprint that the cosmic ray flux is affecting the cloud parameters, which obviously affect the climate because they change the energy budget. This is an experiment, again, which was run in Denmark. You have here a chamber which mimics conditions you find over the oceans. What you see is that when you increase the ionization rate in the chamber, you increase the formation rate of condensation nuclei, basically proving in a lab that if you change or if you play with the density of ions, you will change the formation rate of cloud condensation nuclei, which will later affect the cloud properties. How can we know that if we change the number of cloud condensation nuclei, we affect the cloud properties? What you see here, this is the marine layer of clouds in front of the California and Oregon coasts. And what you see here, these are not contrails of planes, these are ship tracks. Basically what happens is that ships, they burn the dirtiest fuel possible because it's international waters. And then as a result, these the numerous exhaust particles that they emit, they serve as cloud condensation nuclei. So wherever a boat passes, it leaves a trail with many cloud condensation nuclei, and the clouds that you get are whiter because you get more droplets, more numerous droplets, which are smaller and they have a larger surface area. Okay, so basically what we've seen is that ions affect the formation of cloud condensation nuclei, and the changing cloud condensation nuclei changes the cloud cover. We've seen empirical data showing how changes in the cosmic ray flux directly affects the cloud characteristics. Any way you look at it, you see the evidence. Okay, now comes the question. We see qualitatively that there is a link, but we want to know how large is this link, because it's important if you want to understand what is the implications for 21st or 20th century global warming, and of course 21st century climate change. Okay, so first of all, you can look at what the cloud cover changes are actually, or were actually over the past 20 years. And then you can look at the satellite data, which calibrates how much, or using calibrated satellite data, you can know by how much the energy budget has changed due to the change in the cloud cover. And you see that the changes in the cloud cover between solar minimum and solar maximum corresponds to variations in the energy budget, which are about 1 watt per square meter. This should be compared with the 240 watts per square meter, which we get from the sun on average. Not here today, of course. Now, this should be compared with the total change in the solar irradiance, which when averaged over the Earth, gives you a change of 0.17 watts per square meter. So the IPCC, when they want to, or when they say that they take solar variations into account, they just take the solar irradiance, and that's a small effect, okay? In principle, if cosmic rays affect the climate, solar activity affects the climate not with this value, but with this value, which is much larger. Okay, it turns out that you can get to this value with a totally different methods, and the way to do it is to use the oceans as a giant calorimeter to measure how much energy the climate system absorbs and emits every solar cycle. And you can do that with more than one different data set. You can, for example, look at the three-dimensional energy content of the oceans with buoy data, okay, that you have covering all the Earth. You can measure what is the heat content of the oceans as a function of time. You can use the sea level and see how the sea level has changed over time. And the reason that it gives you the heat content is because of thermal expansion. When the oceans heat, they expand. And over the short time scales, it's actually the dominant source of sea level change rates. And you can look at the surface temperature and model it and get what the changes in the heat content is. Basically, we have several methods with which we can see how much heat is going into the oceans and leaving the oceans every solar cycle. And what you find, the different data sets go usually about 50 years, and there's one data set which is much better, and that is the sea level change rate. And what you see here is that you see the solar activity in red, and you see the sea level change rate, basically by how much the sea expands and contracts every 11 years. And you see that the sea is totally in sync with the changes in the solar activity. And by looking by how much the sea expands and contracts, you can actually see that or you can quantify the heat going into the oceans, and quite unsurprisingly, you find that, okay, you can estimate how much heat is going into the oceans every 11-year solar cycle with 3 different data sets. And you can compare that to the heat that you would expect to go into the system with the cloud cover changes. And what you see is that, indeed, the changes in the cloud cover correspond to the same heat that goes into the oceans. Everything is consistent. But this heat that goes into the oceans is much larger than the changes in the solar irradiance. Basically, it tells you that you must have an amplification mechanism. And of course, the cosmic ray flux gives you the mechanism. Not only do you see all the evidence, you can quantify it and see that it operates. Okay, what does it tell us about the 20th century? It tells us the following. First of all, we know that over the 20th century, solar activity has increased. We can look at the total number of sunspots, or we can look at the magnetic field or open magnetic field lines of the sun that we see here. That's over the 20th century. Over longer timescales, you see, for example, the Maunder minimum. That's 300 years ago. The sun was very inactive, and it was much colder in Europe. We know that, or in other places on Earth. But the solar activity has changed. Now, specifically over the 20th century, solar activity has increased, and the change in the cosmic ray flux, or the average cosmic ray flux that you would expect over the 20th century, is similar to the changes between solar minimum and solar maximum. What it tells you is that if you expect energy budget change of about 1 watt per square meter from the cosmic ray flux, or from the cosmic ray flux link, then you would expect a similar contribution over the 20th century because solar activity has increased. Okay. Now, so what we want to do basically is to try and see whether we can explain 20th century temperature change with the effects of the sun. Now, if you open what the IPCC report, well, what you'll see is what is done is the following. Basically, people take what the different components of the radiative forcings are. For example, the contribution of well-mixed greenhouse gases, ozone, solar irradiance, which is very small. And of course, there is the indirect aerosol effects, which nobody knows what it is. It's like a wild card in the game, and you can basically fit whatever you want with this wild card. But when they do that, they say, okay, we can take the components, we can plug it into the global circulation models, we can crank the crank, and then see what we get. And lo and behold, the different models, which you see here in the average in red and the variations of the different models in yellow, can explain the observed temperatures, which are in black. But not everything is rosy with this model. If you look carefully, and this is something which was pointed already a decade ago by Professor Linzen from MIT, you see the following. When you try to explain this type of temperature increase, you need a very large sensitivity. Basically, in order to do that, the climate has to be very sensitive in order to explain the large temperature increase over the 20th century. And as a result of this large sensitivity, when Earth has had large volcanic eruptions, the temperature has decreased by quite a lot. You can see here, the models give you that the temperature should have decreased by quite a lot, like here over Pinatubo. But if you look at what the actual response of the global temperature was in response to these large volcanic eruptions, which put a lot of dust into the stratosphere, you see that when you average the temperature following the 6th largest eruption since Krakatau, you see that the temperature decrease was 0.1 degree. Okay, but the models give you typically 0.3 to 0.5 degrees. So the models are overly sensitive. And you can see that with the third assessment report's graph, not with the fourth assessment report, because in the fourth assessment report, they cut the years before the 1900s, but in the third assessment report, they did fit for a longer time span, and then you can see how embarrassing the fit to the Krakatau eruption is. Basically, all the models give you that the temperature should have decreased by quite a lot, whereas in fact, Earth's temperature wasn't even tickled by Krakatau. Okay, that's because the models are very sensitive. Now, you can, if you want, play a game. You can say, let's try to build a model which takes into account the cosmic ray flux. You can allow for diffusion. You say that the sensitivity is a free parameter. You allow interaction between the land and ocean. You leave everything as a free parameters. And then you ask which parameters can be, for which parameters do you, okay, well, for each parameters that you guess, you can integrate the model and get some predicted temperature as a function of time. And then you can compare it to the observed temperatures, optimize it with some mechanism, for example, a genetic algorithm. And then you find the model parameters that will give you the observed temperatures. And when you play this game, what do you find? You find that, lo and behold, you can find model parameters that can explain the temperature increase over the 20th century very nicely. In fact, the residual, when you try to do that, is twice as good as when you do it with the heavy machinery, with the GCM models. Okay? And you don't get the problems with over-predicting the temperature decrease during volcanic eruptions and things like that. Okay? When you do that, you find that when you try to objectively find which model parameters give you the best fit, you find that indeed the sun must have an indirect effect, and the contribution over the 20th century is roughly what we expected from the cosmic ray flux climate link. That's on one hand. The sensitivity is left as a free parameter. It's not like GCMs where it's an inherent parameter in the model. Here it's a free parameter. And you find that if you want to explain the 20th century temperature change with the least residual, namely to get the best fit, you find that you need models which have no feedbacks, no net feedbacks, no positive feedbacks or no large negative feedbacks, or feedbacks which cancel each other. Basically, Earth behaves like a black body, not something which is amplified. Okay, what does it imply? It implies the following. The standard picture is the following. We have some kind of changes in the energy budget that we humans are associated with, CO2 and other things. And then if we want to explain the large temperature increase over the 20th century, we need a high climate sensitivity. We multiply the forcing with the sensitivity to get how much the temperature increase over the 20th century is. If you have lower forcing, because you have less natural contribution, you'll need a higher climate sensitivity to get this thing. The high climate sensitivity, which you get from the GCMs, then predicts large temperature increase over the 21st century. But if you're saying that you have additional forcings, if the sun affects the climate as well, then the total forcing is larger. If the total forcing is larger, in order to explain the 20th century temperature increase, you need a smaller climate sensitivity. This smaller climate sensitivity gives you a lower temperature increase over the 21st century because Earth is less sensitive. Okay, so we can take the model parameters or the range of model parameters which fit the temperature increase and ask, we can ask how much temperature increase is human or in solar over the 20th century. But we can also take the IPCC scenarios for the emissions and integrate over the 21st century and ask by how much is the temperature going to increase if we manage to, for example, double the amount of CO2. Here, of course, we don't know what the solar activity will be doing, so we have to make realizations for solar activity, volcanic eruptions, etc., and you get a range of models. For comparison, these are the predictions by the IPCC. Okay, so I'll summarize. The sun affects the climate through cosmic rays. You have numerous pieces of evidence which shows you that the cosmic rays are affecting the climate. You can quantify this link and see that this link is very large. This large link implies that the solar activity increase over the 20th century must have contributed a large radiative forcing contribution to the warming. And as a result, you need a lower sensitivity to explain the 20th century warming, but the same lower sensitivity also implies that the temperature increase over the 21st century, if we manage to double the amount of CO2, is going to be modest. And with this, I'll end.